Just beyond Neptune, a vast cosmic frontier holds secrets older than the planets. This is the Kuiper Belt, a distant realm of frozen worlds that has challenged everything we thought we knew. In this journey, we will uncover 25 of its most enigmatic objects, each one a mysterious relic from the dawn of our solar system. By the end, you will discover why these distant specks of light are forcing a complete rewrite of our cosmic history. We will encounter a dwarf planet with a beating heart of ice and an ancient snowman shape that should not exist. What forgotten story does our own solar system's backyard hold? Our first intimate glimpse into this frozen realm came not from a giant world, but from a tiny, primordial fossil named Arrokoth. The New Horizons spacecraft, after its historic flyby of Pluto, raced onward to meet this distant object, revealing a shape that defied simple explanation. There, floating in the deep black, was a cosmic snowman. Arrokoth is not a single sphere, but two distinct lobes pressed gently together, as if two separate bodies decided to merge in a slow-motion dance billions of years ago. Its surface is a startlingly smooth and uniform red, the color of ancient brick, untouched by the violent chaos that shaped the inner planets. This lack of craters and its gentle contact suggest a remarkably peaceful origin. Arrokoth was not born from a violent collision, but from a gentle accumulation, a whisper of a process where tiny particles of ice and dust coalesced in the solar system's quietest nursery. This pristine condition makes it a time capsule, a direct relic from an era before planets even existed. Its very structure is a frozen moment, capturing the exact way the building blocks of worlds first came together. What other ancient construction plans are still floating out there, waiting to be read? That gentle dance of primordial bodies stands in stark contrast to the dynamic and complex world that first drew our eyes to the Kuiper Belt. Pluto, the king of the dwarf planets, is anything but a simple ball of ice. Far from being a static fossil, it is a world of breathtaking activity. Its thin, hazy atmosphere stretches for miles above the surface, a delicate blue envelope of nitrogen with whispers of methane and carbon monoxide. This atmosphere creates winds that sculpt the surface, and its layers of haze form a dramatic alien twilight. But the true engine of this world, its most iconic feature, is the beating heart known as Sputnik Planitia. This vast heart-shaped basin is a sprawling glacier of solid nitrogen, larger than the state of Texas. This is not a frozen, inert slab. It convects slowly like a pot of thick soup on a low simmer, with blobs of warmer ice rising to the surface while older, colder ice sinks. This constant churning motion renews the surface, erasing impact craters and making this heart the youngest landscape on Pluto. This relentless geological activity points to an even more profound possibility deep within. The immense weight of that nitrogen ice, combined with heat from radioactive elements in Pluto's rocky core, may be enough to maintain a vast liquid water ocean trapped between the ice shell and the core. The existence of this hidden sea would fundamentally change our understanding of what it means to be a dwarf planet, suggesting that even in the solar system's deep freeze, worlds can harbor the ingredients for life. This very complexity is what fuels the passionate, ongoing debate about Pluto's status. Is it truly just a dwarf planet, or is it the prototype for a whole new class of complex, ocean-bearing worlds at the edge of our solar system? The debate itself proves that Pluto is far more than a distant footnote. It is a living, breathing puzzle that continues to challenge our definitions and capture our imagination. While Pluto was captivating us with its beating heart, a distant challenger was already rewriting the rules of our solar system. Eris, a world discovered in 2005, was the catalyst for the most dramatic astronomical debate in generations. It was found lurking almost 3 times farther from the Sun than Pluto, a brilliant speck in the data that immediately demanded an explanation. Initial measurements suggested it was even larger than Pluto, a fact that sent shockwaves through the scientific community. If Pluto was the 9th planet, then what did that make this new, seemingly larger world? Eris forced our hand. We could no longer operate with a vague definition of a planet. The discovery revealed an object on a wildly eccentric orbit, swinging from a distance of about 97 astronomical units from the Sun to a far point nearly 100 times the Earth-Sun distance. This path is so extreme that it takes Eris over 550 years to complete a single journey around our star. Its existence, along with the growing number of other sizable Kuiper Belt objects, presented a simple but profound question. Where do we draw the line? The result was the controversial decision by the International Astronomical Union in 2006 to create a new category, the Dwarf planet, a classification that included both Eris and Pluto. This was not a demotion in the eyes of science, but a reclassification born of new understanding. Eris proved that Pluto was not a unique outlier, but simply the first of its kind that we happened to find. It is the celestial key that unlocked a deeper truth, showing us that the outer solar system is not empty, but populated by a whole family of significant worlds. The great planetary debate was never really about Pluto's importance, but about our need to categorize a cosmos that is far more complex and wondrous than we ever imagined. What other fundamental truths are still waiting for their own Eris to reveal them? The discovery of Eris forced us to draw new lines, but Makemake quietly blurred them. This reddish, Pluto-sized world is a solitary figure, named for the creation deity of the Rapa Nui people, and for years it appeared to be utterly alone in the dark. Its surface, coated in frozen methane, gives it a distinct Easter egg hue, a brightly colored world against the black velvet of space. For a decade, we saw it as a simple, if large, frozen sphere. Then, in 2016, the Hubble Space Telescope spotted a faint companion. A tiny moon, now known as MK2, was dancing around Makemake. This was not just a new moon, it was a profound puzzle. The moon is incredibly dark, as black as charcoal, while Makemake itself is brilliantly bright. How can two objects born from the same material and orbiting so close together have such drastically different surfaces? One theory suggests that the sun's feeble warmth at that incredible distance is just enough to vaporize the bright methane ice on the surface of the tiny moon, leaving behind a dark, tar-like residue of heavier organic compounds. This process, akin to a cosmic distillation, would leave the little moon cloaked in darkness while its parent world retains its shiny frost. The very existence of MK2 also raises a bigger question about the Kuiper Belt itself. We keep finding moons around these distant dwarf planets. Pluto has 5, Eris has 1, Haumea has 2, and now Makemake has 1. This suggests that moon formation is not a rare event in the outer solar system, but a common, perhaps even inevitable, part of how these larger Kuiper Belt objects are built. Yet, for all its similarities to Pluto, Makemake lacks one key feature, a significant atmosphere. When it passed in front of a distant star, an event astronomers call a stellar occultation, there was no telltale flicker, no gradual dimming of the starlight that would indicate a surrounding haze of gases. This tells us that Makemake cannot hold onto the volatile ices that, on Pluto, sublimate and create a temporary atmosphere. Its gravity is either too weak or its reservoir of these light ices is simply depleted. So we are left with a beautiful paradox, a world that looks like a twin to Pluto in size and composition, yet behaves in a completely different way. It is a reminder that out in the Kuiper Belt, no two worlds, no matter how similar they may seem, tell exactly the same story. Haumea shatters every expectation of what a round world should be. This dwarf planet spins with such ferocious speed that it has been stretched into the shape of an egg, or perhaps a flattened cosmic football. It completes a full rotation in less than 4 hours, a dizzying pace that creates immense centrifugal force. whipping its once spherical form into a distinct ellipsoid. This rapid spin is the key to its other great mysteries. Astronomers watched in astonishment in 2017 as Haumea passed in front of a distant star. Instead of the star simply blinking out, it flickered both before and after the main event. That flicker revealed the presence of a thin, dark ring of debris orbiting the dwarf planet. This made Haumea the first object in the Kuiper Belt ever discovered to have a ring system, a feature once thought to be the exclusive domain of giant planets like Saturn. But the strangeness does not end there. Haumea is also apparent with two small, rapidly orbiting moons named Hiaka and Namaka. These moons are thought to be chunks of Haumea itself, blasted into orbit by a colossal impact billions of years ago. The evidence for this ancient violence is written across the sky. Haumea is the central member of a collisional family, a group of over a dozen smaller, icy fragments that share nearly identical orbits and compositions. They are all that remains of the other body in that primordial crash, the scattered children of a single, shattering event. This family portrait suggests a dramatic history, a time of immense chaos where worlds collided and reformed in the darkness. How many other battered and reshaped objects are still waiting to tell their stories of ancient cosmic violence? Quaoar presents a paradox as deep as the space it inhabits. Here is a world smaller and colder than Pluto, yet it shows signs of a geological liveliness that seems to defy the bitter cold of the Kuiper Belt. Recent observations have revealed something extraordinary on its surface, patches of crystalline water ice and ammonia hydrates. These are not just any ices, they are the telltale signatures of cryovolcanism, a process where a world's internal heat forces a slush of water, ammonia, and other antifreeze compounds to erupt from its interior onto the surface. For this to happen on Quaoar, there must be a source of warmth, enough to maintain a layer of liquid or at least a warm, malleable slush deep beneath its frozen crust. The most compelling explanation is a subsurface ocean, a vast, dark sea trapped between layers of ice. This suggests that Quaoar, against all odds, might be a geologically active world. Its single known moon, Waywatt, offers another clue to this world's history. This small, irregular satellite orbits its parent at a respectful distance, and its very existence hints at a violent past. Waywatt is likely a fragment of Quaoar itself, chipped off in a colossal impact that also reshaped the dwarf planet. That ancient violence could have provided the initial heat to set a subsurface ocean in motion, a warmth that radioactive elements in its core might still be helping to maintain. The presence of such a world so far from the sun forces us to reconsider the very definition of a habitable zone. Liquid water, the essential ingredient for life as we know it, may not be a privilege reserved for the inner solar system. It could be bubbling away in hidden reservoirs across the Kuiper Belt, locked inside frozen worlds warmed only by their own internal fires. If Quaoar can hold an ocean, then how many other distant, dark worlds might be doing the same? Far beyond the familiar dance of the Kuiper Belt, an object moves in a profound and lonely silence. This is Sedna, a world of reddish ice on an 11,400-year journey around the Sun. Its orbit is a staggering ellipse, a cosmic marathon that takes it from a point still beyond Neptune to an unimaginable distance of over 930 times the Earth-Sun separation. At its most distant, the Sun would be little more than the brightest star in a perpetually black sky, a pinprick of light too faint to cast a shadow. This path is so exceptionally elongated that it defies easy explanation. Nothing in our current model of the solar system can naturally place an object on such a trajectory. Sedna never comes close enough to Neptune or any other giant planet to have been flung outward by their gravity. So how did it get there? The leading theories are as dramatic as the orbit itself. One compelling idea suggests that in our solar system's wild youth, a rogue planet, an orphan world ejected from another star system, may have passed through our outer realms. The gravitational tug from this interstellar visitor could have violently perturbed Sedna's path, hurling it onto its lonely course before the intruder vanished back into the void between the stars. An even more tantalizing possibility is that Sedna is feeling the influence of a permanent resident, a massive, undiscovered planet lurking in the extreme outer darkness. This hypothetical world, often called Planet 9, would have an immense orbit of its own, and its steady gravitational pull over billions of years could shepherd objects like Sedna into their strange, detached paths. Sedna is therefore more than just a solitary world, it is a celestial signpost. Its impossible orbit points toward something we cannot yet see, hinting at a hidden architecture to our solar system, a grand design that we are only just beginning to perceive. Gong Gong presents a world painted in deep, rusty red, a color that speaks of ancient and complex chemistry on its frozen surface. This distinctive hue is likely the result of tholins, complex organic molecules that form when simple ices like methane are bombarded by cosmic radiation over billions of years. The presence of these reddish deposits suggests that Gong Gong has a surface rich in methane, a volatile ice that should have long since escaped from such a relatively small world. Its ability to retain this material marks it as a significant and intriguing body. As one of the largest known denizens of the scattered disk, that chaotic region of space where objects have been flung into wild, tilted orbits by Neptune's gravity, Gong Gong is a testament to the dynamic violence of the solar system's past. But its true strangeness is revealed in its dance with its moon, Xiangliu. This is not a simple orbital partnership. Xiangliu is locked in a synchronous rotation, meaning the same side of the moon always faces its parent world, much like our own moon does with Earth. Yet the orbit itself is unusually elongated and tilted, a messy and chaotic-looking path that implies a turbulent history. This peculiar orbital ballet suggests that Xiangliu was not born alongside Gong Gong from a gentle disk of debris. Instead, it was most likely captured, a celestial passerby that was gravitationally snared during a close encounter in the deep past, locking them both into this perpetual, lopsided waltz. The existence of such a large moon around a scattered disk object is yet another clue that these distant realms are not just collections of solitary ice balls, but complex systems with their own unique histories of collision and capture. What other mismatched pairs are waltzing in the darkness, their orbits telling tales of ancient gravitational heists? Orcus completes a cosmic dance with Neptune, a mirror image of Pluto's own rhythm. This distant dwarf planet is locked in the same resonant orbit, completing 2 circuits around the Sun for every 3 that Neptune makes. But while Pluto and Neptune are in a kind of gravitational sync, Orcus is always on the opposite side of the Sun, a counterbalance in the darkness. This precise celestial choreography has earned it a dramatic nickname, the anti-Pluto. It is as if the solar system designed a perfect pair, 2 worlds linked by an invisible gravitational thread, forever separated by the star they orbit. But Orcus is not alone in its distant phase. It is accompanied by a surprisingly large moon named Vanth. This companion is not a tiny speck. It is a substantial world in its own right, so large relative to Orcus that they almost form a binary pair. The 2 orbit a common center of gravity, a point in the space between them, locked in a tight, slow waltz. Vanth's surface is unusually dark, a stark contrast to the brighter ice of Orcus, suggesting they may have very different origins and compositions. This stark difference fuels a compelling mystery. Was Vanth born from a colossal impact with Orcus, a chip off the old block? Or was it a completely independent object that was later captured by the dwarf planet's gravity? The answer is written in their orbital dance and their contrasting faces. If Vanth was captured, it tells a story of a chaotic early Kuiper Belt where gravitational encounters were common. If it was born from impact, it reveals that even out here, worlds were smashing together to create families. The Orcus-Vanth system is a frozen laboratory, a preserved record of the gravitational and collisional processes that built our solar system's final frontier. What other mirrored worlds and their dark companions are waiting to be found, each pair telling its own version of this ancient story? Ixion emerges from the darkness as a question mark painted in deep red. This potential dwarf planet is a classic Plutino, one of that population of Kuiper Belt objects locked in the same rhythmic dance with Neptune as Pluto itself, completing 2 orbits for every 3 of the ice giant. But its true intrigue lies not in its orbital mechanics but in its color. Ixion's surface is a distinctive, almost rusty red, a hue that speaks of ancient chemistry at work. This coloration is the telltale signature of tholins, complex organic molecules that form when simple ices like methane are bombarded by solar radiation and cosmic rays over billions of years. It is a process akin to leaving a piece of plastic out in the sun for eons, slowly baking and transforming it into something darker and more complex. The presence of these tholins suggests that Ixion has, or once had, a significant reservoir of methane ice on its surface, a volatile material that should have evaporated from an object of its size. This paradox makes it a compelling subject of study. How has it managed to retain these ices, or are we seeing the final, dark residue of a supply that is almost gone? Its surface is a time capsule of cosmic chemistry, a record of the endless interplay between primordial ice and the relentless rain of radiation from space. Ixion, like so many of its distant cousins, is not a static ball of ice. It is a dynamic chemical laboratory, frozen in time, forcing us to ask what other complex organic processes are occurring in the perpetual night of the Kuiper Belt. Varuna whirls through the void in a relentless, dizzying sprint. This distant world completes a full rotation in just about 6 hours, a speed so extreme it has sculpted the object into a distinct ellipsoid, a stretched-out sphere resembling a flattened football. Imagine a ball of soft clay spun rapidly between your hands, how it bulges at the center and flattens at the poles. Varuna experiences that same centrifugal force on a colossal scale, its own gravity struggling to hold it together against the whipping momentum of its spin. This distorted shape is a direct window into the world's internal composition. To be so dramatically stretched, Varuna cannot be a solid, rigid ball of rock. Instead, it must be a relatively loose aggregation of material, a porous pile of ice and rock held together by its own modest gravity. Astronomers calculate its density to be surprisingly low, suggesting it is more of a fragile cosmic rubble pile than a monolithic sphere. Studying such a faint and fast-moving object from Earth, however, is a monumental challenge. We cannot see its shape directly, instead inferring it from precise measurements of its changing brightness. As Varuna spins, its elongated profile presents different faces to us, causing its light to pulse in a regular rhythm. Decoding that subtle flicker from across billions of miles is like trying to discern the shape of a distant car by only watching its blinking headlights. This rapid spin itself is a lingering mystery. What ancient impact or gravitational encounter set this world spinning so violently, and why has it not slowed down over the eons? Varuna stands as a testament to the dynamic and often violent processes that shaped even the smallest denizens of the Kuiper Belt, its frantic dance a permanent record of an ancient chaos. Its official designation is a string of numbers and letters, but this nameless giant is one of the largest worlds we know of in the Kuiper Belt. Known only as 2002 MS4, this object is a titan lurking in the observational shadows, a placeholder for a world that has yet to receive its true name. Its estimated size places it in the same league as many of the named dwarf planets, a massive sphere of ice and rock whose story remains largely untold. What makes this anonymous world so intriguing is its surprising brightness. 2002 MS4 possesses a relatively high albedo, meaning its surface is remarkably reflective. It shines back a significant portion of the tiny amount of sunlight that reaches it, suggesting a crust that is not dark and ancient but fresh and clean. This points to a surface possibly covered in pristine water ice, a landscape that has been recently renewed or is actively being refreshed. Perhaps cryovolcanic processes are at work, oozing new, bright ice from its interior to coat the surface, or maybe its orbit keeps it in a cold, stable state where dark tholins cannot easily form. The very existence of such a large and bright object, still waiting for a name, highlights a fascinating bottleneck in our exploration of the outer solar system. The process of officially naming a celestial body is not automatic. It requires detailed study, a confirmed orbit, and a consensus within the astronomical community. For distant, slow-moving objects like 2002 MS4, gathering enough data to move from a provisional designation to an official name can take decades. It is a world caught in a kind of scientific limbo, too distant for our telescopes to resolve in detail, yet too significant to ignore. It stands as a powerful symbol of how much we still have to learn. Our catalogue of the Kuiper Belt is filled with these provisional giants, each one a silent reminder that the most fundamental step of discovery, the act of naming, still lies ahead of us for some of the largest members of our own cosmic family. The nickname Snow White promised a world of pure, brilliant ice, but the reality was a world cloaked in a deep, dark red. This was the puzzling story of 2007 OR10, a dwarf planet whose appearance completely contradicted its fairy tale moniker. Astronomers had initially expected a bright, icy surface, but instead found one of the darkest and reddest objects in the entire Kuiper Belt. This intense coloration comes from a thick coating of tholins, complex organic sludge created when methane ice is cooked by solar radiation for billions of years. The presence of so much of this dark, reddish gunk meant that 2007 OR10 had to be covered in methane, but there was a problem. Methane is a highly volatile ice, and at this object's distance from the Sun, it should have slowly escaped into space over the eons. So how could it still have enough methane on its surface to create such a dramatic color? The answer arrived with the discovery of its moon. Observations from the Kepler Space Telescope revealed a small companion in orbit, and the presence of this moon helped solve the methane mystery. The moon's gravitational influence likely helps provide just enough extra tug to assist the dwarf planet in holding onto its tenuous blanket of methane, preventing it all from drifting away. This finding transformed our understanding of the object from a solitary enigma into a dynamic system. The story of 2007 OR10 culminated not just in scientific revelation, but in a formal naming ceremony. Following the tradition of naming dwarf planets after creation deities, it was officially given the name Gonggong after the Chinese water god with a fiery temper, a chaotic force who is said to have caused great floods. This name perfectly captures the world's own paradoxical nature, a dark, red, water-rich world existing in the deepest freeze. The journey from the misleading nickname Snow White to the powerful, official name Gonggong is a perfect example of how our understanding of these distant worlds evolves, moving from initial, often mistaken impressions toward a deeper, more nuanced and truly fitting identity. The Salacia system moves with a slow, deliberate grace, a widely separated pair locked in a patient dance. Salacia itself is a sizable dwarf planet candidate, but its true identity is defined by its relationship with its moon, Actaea. These two worlds orbit a common center of gravity so distant it takes them nearly 6 Earth days to complete a single circuit. This is not a tight, frantic waltz, but a sprawling, measured embrace across hundreds of thousands of miles. Their stately orbital separation is a critical clue to their nature, pointing toward an exceptionally gentle origin. The most revealing data, however, comes from their combined density. When astronomers calculated it, they found a value remarkably low, lower than that of water ice. This is not the density of a solid, compact sphere of rock and ice. Instead, it suggests a world and its moon that are essentially porous rubble piles, collections of icy fragments held together loosely by their own feeble gravity. They are more like cosmic snowdrifts than hard, monolithic stones. This fragile, fluffy composition is a direct window into the conditions of the early Kuiper Belt. Salacia and Actia were not forged in a violent collision. They almost certainly formed together from a slow, gentle accumulation of smaller particles in the primordial cloud of dust and ice that surrounded the young sun. Their wide orbit and low density imply that they coalesced from this cloud without ever experiencing a dramatic, planet-shattering impact, preserving their delicate, primordial structure for billions of years. The Salacia system is a fossilized example of the quietest, most peaceful method of world building. It shows us that not all cosmic construction was chaotic and violent. Some worlds were whispered into existence, and their gentle, spacious dance is the enduring echo of that ancient, quiet process. How many other such fragile, binary fossils are still drifting in the dark, preserving the softest whispers of the solar system's birth? DD emerged from the darkness as a testament to how much we are still learning about our own cosmic neighborhood. Its official name is a catalog number, 2014 UZ224, but its nickname came from its initial classification, distant dwarf. This world was discovered in a most unlikely way, not by a telescope dedicated to hunting planets, but by the Dark Energy Survey, a project designed to study the accelerating expansion of the entire universe. In the midst of mapping the most profound forces in the cosmos, it inadvertently spotted a tiny, slow-moving speck within our own solar system. Confirming DD as a substantial world, however, required a different kind of eye. The powerful Atacama Large Millimeter Array, or ALMA, turned its antennas toward this faint point of light. ALMA does not just see visible light, it observes the universe in radio waves, allowing it to detect the faint heat signature of cold, distant objects. By measuring this thermal glow, astronomers could finally calculate DD's true size. They discovered it was over 400 miles across, a diameter that almost certainly makes it a round dwarf planet. But its most telling feature was its profound darkness. DD reflects very little of the sun's feeble light, which means its surface is not a bright, icy landscape, but likely coated in a layer of dark, complex hydrocarbons, the same kind of tholins that paint other Kuiper Belt objects in shades of deep red and black. This combination of large size and extreme darkness is what makes DD so significant. It is not a brilliant outlier, but a shadowy representative of a vast, hidden population. If a world this large remained unknown until just a decade ago, how many other dark giants are still drifting unseen in the outer blackness, their presence betrayed only by the faintest whisper of their own heat? 2004 XR190, nicknamed Buffy, moves through the void on a path that should not be possible. While most objects in the Kuiper Belt orbit in roughly the same flat plane as the planets, Buffy carves a dramatic high-inclination track, soaring high above this common disk before plunging back down below it. Its orbit is not only tilted but also remarkably circular, a combination that defies our standard models of solar system formation. How did this world get thrown so dramatically off track without being flung entirely out of the system or sent on a wildly elongated path? The gentle gravitational nudges from Neptune, which sculpted so many other Kuiper Belt orbits, seem incapable of this kind of precise, violent lifting. This has forced astronomers to consider far more dramatic events in the solar system's wild youth. One compelling theory points to a grand reshuffling of the giant planets. In this model, known as the Nice model, Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. They migrated outward, their gravitational influence churning the outer solar system like a spoon through thick soup. It is possible that during this chaotic era, a resonance, a specific gravitational rhythm between the migrating planets, could have acted like a cosmic slingshot, plucking Buffy from the primordial disk and launching it onto its highly inclined yet circular highway. An even more spectacular possibility involves an interstellar visitor, a star passing relatively close to our young solar system, perhaps within a few hundred astronomical units, could have reached out with its gravity, stirring the outer debris disk and kicking a number of objects like Buffy onto these strange, tilted orbits before continuing on its journey into the galactic dark. Buffy's lonely, elevated path is a potential fossil record of that ancient stellar flyby, a permanent scar from a close encounter that happened over 4 billion years ago. This single object, with its impossible orbit, forces us to look beyond our own solar system for answers, suggesting that our cosmic neighborhood was not born in isolation, but was shaped by interactions with the wider galaxy. The faintest of cosmic phantoms, a world known only as 2015 TG387, drifts in a realm of near-total darkness. Its nickname, the Goblin, is perfectly suited, for it is a ghost of the outer solar system, appearing only under the most specific conditions. This small, icy world was discovered at an astounding distance of about 80 astronomical units, nearly 3 times farther from the Sun than Pluto. But its discovery was a feat of celestial timing and patience. The Goblin was only visible because it happened to be at the closest point of its immensely long orbit, a fleeting moment of relative proximity that allowed our telescopes to catch a glimpse before it began its long retreat back into the abyss. Its full orbital path is a staggering ellipse that takes an estimated 40,000 years to complete, carrying it to an almost unimaginable aphelion, its farthest point from the Sun, of over 2,000 astronomical units. At that distance, the Sun is reduced to a mere pinpoint, just one star among many in a perpetually black sky. An orbit this vast and elongated cannot be explained by the gravitational influence of the known planets. Something else, something massive and unseen, must be shepherding it, preventing its path from being random. The Goblin's orbit is not unique, however. It shares a peculiar geometric alignment with other extremely distant objects like Sedna. Their orbits are clustered in space, as if an invisible hand has gathered them together, their farthest points all pointing in roughly the same direction. This clustering is the most compelling evidence yet for the existence of Planet 9, a hypothetical giant planet whose distant gravity orchestrates the motion of these smaller worlds. The Goblin, therefore, is far more than a solitary ice ball. It is a celestial compass. Its impossible path points directly toward a shadow in our maps, a ghost guiding us toward a far larger ghost. Finding such a faint object at the very edge of our observational capabilities is like spotting a single, distant candle flame and using its faint flicker to deduce the existence of an entire hidden continent. What other faint whispers from the dark are we only now learning to hear? 208 ST-291 is a ghost in the data, a world so faint and distant that simply confirming its existence was a triumph of modern astronomy. This object, one of the farthest known members of the scattered disk, pushes our telescopic vision to its absolute limit. Its light is barely a whisper, a photon here and there collected over hours of exposure time to create a single blurry pixel. From this faint glimmer, we can infer its presumed size, likely several hundred miles across, and its profound darkness, a surface that reflects almost none of the Sun's feeble light. This combination tells a crucial story about the demographics of this chaotic region. The scattered disk is not just a collection of a few bright, famous worlds. It is a vast expanse populated by countless dark, moderate-sized objects like 208 ST-291, each one a shadowy testament to the gravitational scattering that occurred billions of years ago. These faint candidates are the true majority, the silent backbone of the outer solar system. Why are they so crucial to our understanding? Because every single one, no matter how dim, adds another day to point to our map of the Kuiper Belt's true extent and mass. Finding these faint objects is like trying to take a census of a country by counting only the people standing under bright streetlights. If we only count the Plutos and the Erises, we are missing the vast, dark population that lives in the shadows between them. Each new discovery, like 208 ST291, helps us weigh the entire Kuiper Belt, allowing us to calculate how much material was left over from the solar system's formation. This total mass is a critical clue. Does it match what our models predict for planet formation, or is there a glaring discrepancy, hinting that much more material was ejected or stolen in the solar system's chaotic youth? The faintest points of light are therefore the keys to the grandest questions, their dim glow illuminating the total weight of our cosmic backyard and the violent history that shaped it. 205 RN43 is a silent giant, a world built from the original blueprints of the solar system. With an estimated diameter of over 450 miles, it ranks among the largest known objects in the Kuiper Belt, a substantial sphere of primordial ice and rock. Its surface is a canvas painted in the subtle colors of deep space, displaying a neutral to slightly reddish hue. This is not the dramatic red of Tholen seen on other worlds, but a more muted tone that speaks of a different history. The composition here is dominated by water ice, a fundamental building block of the outer solar system, preserved in an almost pristine state. This lack of dramatic coloration suggests a surface that has been relatively untouched by the radiation-driven chemistry that creates complex organic sludge on other objects. 205 RN43 appears to be a clean, frozen relic, a time capsule that has avoided the dramatic collisions or internal heating that have reshaped so many of its neighbors. Its very blandness is its greatest secret. This world is like a page from the very first chapter of our solar system's story, a chapter written before the plot twists of planetary migration and violent impacts scrambled the narrative. By studying its untouched surface, we are essentially reading the original recipe for a Kuiper Belt object, learning the precise mixture of ices and silicates that were available in this region of the protoplanetary disk over 4 billion years ago. How many other such pristine relics are floating in the dark, holding the pure, unedited record of our cosmic beginnings? 203 AZ84 is a perfect example of a celestial body that refuses to be easily categorized. This substantial world is a Plutino, locked in the same 2 to 3 orbital resonance with Neptune as its more famous cousin, Pluto. This means for every 2 laps it completes around the Sun, Neptune completes 3, a gravitational synchrony that keeps their path stable and prevents close encounters. Yet, for all its orbital predictability, pinning down this object's most basic characteristics has proven incredibly difficult. Its exact size remains a subject of debate, with estimates ranging significantly. The core of this uncertainty lies in a single, fundamental property we cannot directly measure from Earth: its albedo. Albedo is simply how reflective a surface is, and it is the key to unlocking the true size of a distant object. A bright, highly reflective surface can make a small object appear large and brilliant in our telescopes. A dark, low reflectivity surface means a much larger object can appear faint and small. For 203 AZ84, we are stuck in this exact puzzle. We can see how bright it is, but without knowing its albedo, we cannot know if we are looking at a smaller, shiny world or a larger, darker one. This is why the study of its single moon, discovered in 2005, is so crucial. By observing the orbital dance of the moon, astronomers can calculate the system's mass. Combining that mass with a size estimate gives us the density, a vital clue to the object's internal composition and history. Every Plutino like this one is a frozen time capsule from an era of planetary migration. Their very existence, neatly parked in these stable resonant orbits, is considered a fossil record of Neptune's outward journey billions of years ago. As the giant planet moved slowly outward, its immense gravity captured and shepherded countless primordial objects into these synchronized paths, like a comb organizing strands of hair. By studying the sizes, masses, and compositions of these Plutinos, we are essentially reading a history book written in gravity and ice, a book that details the final, dynamic steps in the construction of our solar system's architecture. How many other resonant worlds are holding the precise measurements of that ancient planetary dance? The puzzle of 2002 UX25 is not what it contains, but what it lacks. This object and its moon possess a density so astonishingly low that it defies simple explanation. The calculated number is less than half that of water ice, a figure that seems physically impossible for a solid world. If you could somehow place this entire system in a cosmic ocean, it would not sink but float, bobbing on the surface like a piece of porous pumice stone. This is not the density of a compact ball of rock and ice. It points to a structure that is overwhelmingly empty space, a fragile, porous rubble pile held together by the faintest of gravitational grips. The material itself is likely dominated by water ice, but it is not solid. Instead, it is a loose aggregation of countless icy fragments with vast gaps and voids between them, a celestial sponge frozen in the deep cold. This extreme porosity presents a direct challenge to our models of how mid-sized Kuiper Belt objects evolve. Conventional wisdom suggested that over billions of years, the relentless pull of gravity and the heat from radioactive decay would slowly compact these worlds, squeezing out the voids and turning them into denser, more solid bodies. Yet here is 2002 UX25, a world several hundred miles across that has stubbornly resisted this process. It has retained its delicate, feather-light architecture since the solar system's birth. How could such a fragile structure survive for so long without collapsing under its own weight or being shattered by impacts? The answer may lie in the gentle nature of the Kuiper Belt itself. Far from the sun, in that deep freeze, the forces acting on these worlds are minimal. Without significant internal heat or frequent violent collisions, there is simply no pressure to compact the material. 2002 UX25 is a preserved relic of a gentler construction method, a world built not by force, but by a slow, gentle accumulation of icy pebbles and dust that never fully packed down. Its very existence suggests that this porous, fragile state may be the rule for mid-sized objects, not the exception. What does it mean for our solar system if so many of its distant building blocks are not solid spheres but fragile, floating snowdrifts? Before we knew the scattered disk existed, a lonely object named 1996 TL66 was quietly mapping its territory. This world was a true pioneer, one of the very first of its kind ever spotted by astronomers, and its discovery was a quiet revolution. Its orbit was the key, a wild and untamed path unlike the relatively orderly tracks of most Kuiper Belt objects. It swung on a highly eccentric journey, taking it from the outer reaches of the Kuiper Belt to a distant point far beyond, and its orbit was also sharply inclined, tilted high above the common plane of the solar system. This was not just a new object, it was a new category of existence. 1996 TL66 was a messenger, and the message was that the solar system did not have a neat, clean edge. Instead, it had a chaotic, sprawling frontier, a region we now call the scattered disk. This revealed a population of objects that had been violently evicted from their original orbits near Neptune and flung into these wild, looping paths by the giant planet's gravity. They were the cosmic refugees of a planetary migration that happened billions of years ago, their scattered orbits telling a story of gravitational upheaval. Finding this single object was like discovering a single arrowhead in a field and realizing it points to an entire, forgotten civilization. It forced our maps to grow, pushing the known boundaries of our own cosmic neighborhood outward and revealing a solar system far more dynamic and extensive than we had ever dreamed. If a pioneer like this could redefine our backyard, What other cartographic revolutions are still waiting in the dark? The story of 1995 SN55 is a cosmic detective tale of loss and rediscovery. This object was first spotted in the autumn of 1995, a faint point of light moving against the background stars. Astronomers recorded its position, calculated a preliminary orbit, and then, as is common with such fleeting discoveries, moved on to other targets. The initial data was sparse, just a few observations over a short arc of its immense journey. Without enough points to accurately plot its long-term path, the object's orbit was too uncertain to reliably predict where it would be in the future. Over the following years, as telescopes searched for it again, 1995 SN55 was nowhere to be found. It had vanished back into the impenetrable darkness of the outer solar system, becoming a lost world. For nearly 2 decades, it remained missing, a ghost in the catalogs. Its recovery required patience, improved technology, and a dedicated hunt. Astronomers had to calculate where it should be based on the old, uncertain data, and then painstakingly scan vast areas of sky, looking for that one faint, moving speck. The successful rediscovery was a triumph of persistence, finally pinning down this wanderer's true orbit and securing its place in our maps. This entire saga underscores a fundamental challenge in Kuiper Belt science. These objects move so slowly against the sky that determining a precise orbit requires observations spread over many years, sometimes decades. A single, short observation arc is like seeing a car for just 1 second as it passes a single streetlight. You know it was there, but you have no idea what road it was on or where it was headed. Only by watching it pass multiple streetlights can you trace its true route. This is why long-term observational campaigns are the unsung heroes of astronomy. They provide the relentless, patient data collection that turns a one-time sighting into a permanent resident of our cosmic understanding. Every recovered object like 1995 SN55 is a victory against the sheer scale and darkness of space, a reminder that our knowledge of the solar system is built not just on brilliant flashes of discovery, but on the slow, steady work of never letting go. Its path is a steep climb out of the solar system's common plane, a tilted track that marks it as an outsider. This is 1999 CD158, an object whose orbit is dramatically inclined, carrying it high above and far below the flat disk where most planets and Kuiper Belt objects reside. Such a steep angle is a clear signature of a violent past, a gravitational wound inflicted long ago. This world did not form in this wild, looping path. It was born in the relatively calm, flat protoplanetary disk alongside countless other icy bodies. But then came Neptune. As the ice giant migrated outward in the solar system's youth, its immense gravity acted like a cosmic slingshot, flinging any object that ventured too close onto a new, chaotic trajectory. For 1999 CD158, that close encounter did not just change the shape of its orbit, it kicked the entire orbit up, tilting it like a misaligned record on a turntable. This process, known as gravitational scattering, is the primary force that created the entire scattered disk population. These objects are the refugees of that ancient planetary migration, their wild orbits serving as permanent records of their close brush with a giant. But why do some objects get these high inclinations while others remain in the flat plane? It all depends on the precise angle and distance of that fateful encounter with Neptune. A gravitational nudge from just the right direction can impart that vertical kick, sending a world on a journey that soars high above the orderly dance of the inner solar system. Every time we find an object like 1999 CD158, we are reading another entry in Neptune's migration diary, another timestamp from an era when the outer solar system was a chaotic construction zone. What other tilted paths are still waiting to be traced, each one a unique fossil of our solar system's most dynamic era? Long before we knew the names Arrokoth or Eris, there was a quiet confirmation in the dark. 1993 SC was one of the very first Kuiper Belt objects discovered after Pluto and its moon Charon, a faint signal that proved a theoretical frontier was real. For decades, astronomers had predicted a disk of icy material beyond Neptune, a reservoir for short-period comets and a relic of the early solar system. But prediction and proof are worlds apart. The detection of this small, distant world was that proof. It was not just another asteroid or a lonely outlier. It was a representative of a vast, unseen population. Its discovery in 1993, made with a telescope in Hawaii, shattered the old idea of a quiet, empty space beyond the planets. Suddenly, the solar system felt much larger. This was the key that unlocked the gate. The confirmation of the Kuiper Belt's existence did more than just add new objects to a catalogue. It opened an entirely new field of planetary science. We could no longer study the outer solar system as a set of individual curiosities. We had to understand it as a structured region, a dynamic belt with its own history, architecture, and population dynamics. Every discovery that followed, from the dwarf planets to the scattered disk wanderers, traces its lineage back to these first few detections. 1993 SC stands as a quiet monument to a pivotal shift in human knowledge. It is the humble beginning that made all the other mysteries possible, a single point of light that illuminated an entire cosmic continent waiting to be explored. What other theoretical frontiers, currently just lines on an astronomer's chalkboard, are waiting for their own 1993 SC to make them real? From dwarf planets hiding subsurface oceans to solitary wanderers on impossible orbits, the Kuiper Belt reveals itself as a realm of staggering diversity. Each of these 25 objects tells a different chapter in the solar system's untold history. We have encountered worlds shaped by gentle whispers of accumulation and others scarred by ancient violence, solitary giants cloaked in darkness and binary pairs locked in a slow dance. This is not a static museum of frozen fossils. It is a dynamic, living frontier where geology defies the cold and gravity paints pictures of unseen planets. The very existence of these objects, from the cosmic snowman Arrokoth to the ringed oddity Haumea, forces us to rewrite our textbooks. They prove that the outer solar system is a place of constant surprise, a region teeming with secrets that challenge our most fundamental assumptions about how worlds form and evolve. Our journey through this cosmic backyard is just beginning. With every new observation, every faint speck of light recovered from the darkness, we pull back another layer of this profound mystery. So we turn the question to you. Which of these enigmatic objects captured your imagination the most? Was it Pluto with its beating heart of nitrogen, the lonely wanderer Sedna on its 11,000-year journey, or the ghostly Goblin pointing toward a hidden giant? Let us know in the comments and subscribe to continue exploring the deepest mysteries of space together.